Hello and welcome to STEAM Explore and Design Thinking. My name is Tushar Murthy and I'll be your host for today's lesson, Punkin Chunkin. We're going to build a mini trebuchet to launch marshmallows. Let's take a quick look at a video of a trebuchet in action. The picture you see is a trebuchet. A trebuchet is a medieval siege weapon used to throw projectiles at or over walls of a city or a castle. It could be used offensively to either knock down castle walls and take control, or it could be used defensively to protect the castle from invaders. Trebuchets were often made of wood and had wheels so that they could be transported to the ideal launching point. Projectiles were launched either by having many people pull down on the short end of the arm, or by dropping a heavy counterweight, usually a basket of stones. Today, trebuchets are still used for recreation. They can be made of wood or metal. In a challenge known as Punkin Chunkin, some participants use trebuchets to launch pumpkins. Today we're going to assemble a mini trebuchet. Let's make some observations about how a trebuchet works using the concept of leverage. A trebuchet has a long throwing arm with a heavy weight on one end and a sling that holds a projectile, for instance a pumpkin, on the other end. The long throwing arm is called the lever arm. The lever arm is a critical part of the concept of leverage. We're going to learn about leverage and how we can apply leverage to launch objects. While it would be really fun to build a huge trebuchet like we saw in the video, this room may not be large enough to do that. Instead, we'll build a small prototype, a working mini trebuchet. Are you ready? So what is leverage? Leverage is a way to increase an applied force. One item you need for leverage is a lever arm. But if that lever arm sits on a flat surface, there is no leverage since the lever arm needs something around which to rotate or pivot. That pivot point is called a fulcrum and is represented by that black triangle in the diagram. In this case, I can use my fist as a fulcrum. Observe how the ruler, the lever arm, rotates around that point. If the fulcrum are big and flat, the lever arm can't rotate properly, and if it can't rotate properly, it's not going to generate enough leverage. So ideally, we want that fulcrum to be a perfect point. In this case, it's not a perfect point, but it's narrow enough that the lever arm can rotate around it. So that way, I can actually generate some leverage using a very simple fulcrum and a simple lever arm. So how can we take advantage of leverage? Well, the amount of leverage you get depends on how long the lever arm is on each side of the fulcrum. The longer the lever arm is, where you're applying your force, the more mechanical advantage you can gain, the more you can increase that applied force that you're applying. Let's take the case of two objects, one heavy, one light. If they're sitting on a lever arm and the fulcrum is in the middle, like a seesaw, what do you think will happen? Well, on a seesaw, if one person's heavy and one person's light, the heavy person is going to go down, the light person is going to go up. The heavy object will lift the light object. Neither one has more leverage than the other because they're both the same distance from the fulcrum. Let's take a second case. Imagine that the fulcrum is closer to the light object. Well, now the heavy object has the longer segment of the lever arm, meaning it has more leverage. It also has more weight. So the light object is definitely going to be lifted as the heavy object goes down and the light object goes up. The third case, this is the most interesting case, and that's if the fulcrum were much closer to the heavy object. Now the light object has much more leverage than the heavy object, and it can actually lift the heavy object. Let us review what we've learned so far. Which of the following statements is true? A, leverage is a way to eliminate a force, or B, leverage is a way to increase an applied force. The correct answer is B. Leverage is a way to increase an applied force. And we can use leverage to lift, squeeze, or cut objects that we would not be able to without such mechanical advantage. Here's a second question. Which of the following statements is true? A, the fulcrum is a long bar that rotates around a lever arm, or B, the lever arm is a long bar that rotates around the point of a fulcrum. The correct answer is B. The lever arm is a long bar that rotates around the point of a fulcrum. Think about the lever arm like your arm. It's a long object, right? The fulcrum is a small point that allows a pivot point for that lever arm to rotate. Let's look again at our ruler as a lever arm. In order to really take advantage of leverage, we need to apply our force on the longer side of the lever arm. We want to place the heavy object, the object to be lifted for instance, on the shorter side of the lever arm. For instance here, this is a case where I've got this eraser as a fulcrum, this ruler as a lever arm. I'm going to place this heavy object, a book, on the longer side of the lever arm, applying my force on the shorter side of the lever arm. You can see here that I can't seem to lift this book. Now let's move the fulcrum closer to the heavy object. Look how short the lever arm is on that side. I've got a much longer lever arm, which means that I'm going to be able to generate more leverage. Oh, look at that. Now I can lift the heavy object without much effort at all. And that's the power of leverage. Let's go back to that green person who wants to lift a heavy object. Now that we understand how leverage works, we know that we want to place the heavy object on the short side of the lever arm, and we want to have the green person apply force to the longer side of the lever arm. The green person has more mechanical advantage, greater leverage, and can now lift the heavy object. A quick aside, as when anytime we're studying a new concept, we're going to make some simplifying assumptions. First, let's assume that the fulcrum is a perfect point and is infinitely strong. It won't break depending on how much force we apply. We'll also assume that the lever arm is infinitely strong and that it is weightless. We don't want the length of the lever arm to cause more force or more weight and throw off the balance of that leverage problem that we're doing. So far we've been talking about leverage to lift a heavy object, but the reality is we can see leverage in everyday tools to press, squeeze, or even cut things. Here we see an example of how leverage is used in everyday work. I want to remove this nail from a piece of wood. Pulling it by hand is going to be very, very difficult. But I can use the claw of a hammer or a crowbar. Notice the shape of the tool. The load, the heavy object, in this case the nail, is on the short end. The hammer will pivot, or the crowbar will pivot on this end point here. Look how close the load is to the fulcrum. It's very short. Where am I going to apply my force? I'm going to apply it to this long segment of the lever arm up here in order to generate as much power as possible and extract that nail from the wood. If I had applied the force very close to the fulcrum, this pivot point, I probably wouldn't have been able to pull out that nail. But by sliding my hand all the way up here, I generated enough leverage in order to pull the nail out easily. Another common tool that uses leverage is a pair of pliers. In fact, there are two lever arms, but let's examine just one of those arms to start. The fulcrum is the round hub in the middle. The two sides of the lever arm will rotate around that circle. And just like with the crowbar or claw of a hammer, we see that we apply our manual force to the longer side of the lever arm, while the object to be held or squeezed is placed in the shorter side of the arm. Observing the full tool, we see that there are two lever arms which move in opposite directions around a single common fulcrum. As the top end of the pliers is forced down on the object, the bottom end pushes up on the object. Squeezing the pliers using the longer end of the lever arms allows us to grip or press the object with a large amplified force, much more than we could apply if we used our bare hands. Okay, let's find the correct completion of the following statement. For a smaller force or weight to lift a heavier weight using leverage, A, the smaller force has to be applied to the longer side of the lever arm, B, the fulcrum must be in the center of the lever arm, or C, a fulcrum cannot be used. The correct answer here is A. The smaller force has to be applied to the longer side of the lever arm. If the lighter object or the smaller force on the longer side the heavier object can be lifted. Now for a tougher question. What happens when unequal weights are placed equidistant from the fulcrum, as shown on the screen? Notice that the light weight is on the longer side of the lever arm, but it is not at the end of the arm. In this case, what will happen? A, the light weight will lift the heavy weight. B, the heavy weight will lift the light weight. Or C, the light and heavy weights will remain balanced. The correct answer is B. The heavy weight will lift the light weight. The leverage of a force depends not based on just the lever arm length, but the distance that force is applied from the fulcrum. Let's think about this as scientists. Let's say you're on a seesaw with a heavier friend. Since you're both the same distance from the fulcrum, what's going to happen? Well, your friend will go down, lifting you up. Now, will having more weightless lever arm behind you change anything? No. Your heavier friend is still going to remain down, and you're still going to remain up. That extra lever arm behind you doesn't help unless you move to the back. We're going to do an experiment with a piece of cardboard and a pair of scissors to try to see how we use leverage every day. Before you reach for those scissors, let's talk about what we will do and what we might expect to see. So we're going to try two different ways of cutting a piece of cardboard. First, we're going to open the scissors wide so it has a large mouth and put the cardboard all the way in and try to cut it. Next, we're going to narrow it down so it's a very small mouth, putting the cardboard right at the end of the scissor blade and then try to cut it. We'll try each of these a few different times and we'll observe how easy it was to cut with the scissors wide open and how easy it was to cut the cardboard with the scissors closed down. All right, let's start the experiment. You should have found that the first technique was easier. When we open up the scissors wide and bring the cardboard load as close as possible to the fulcrum of the scissors, that makes it easier to cut it. This ties back to our reasoning that the leverage of the force we apply to cut the cardboard depends on the distance that each object is from the fulcrum. It does not depend on the total lever arm length if the objects are not at the ends of the lever arm. Although we cannot change the lever arm length where we apply the force from our hand, the handles, we can reduce the leverage of the cardboard's resistive force by bringing it closer to the fulcrum, shortening its lever arm length. So up to now we've talked about lighter objects lifting heavier objects using leverage, but we haven't quantified how heavy is heavy, how light is light, how long does the lever arm need to be. So we're going to do that here. What we found through energy considerations as well as corroborated by measurements is that the product of force and distance on one side of the lever arm has to equal to the product of force and distance on the other side of the lever arm. The product of force is just the multiplication. F times d on one side has to equal to F times d, the force times distance, on the other side. With this formula, now we can compute exactly how much force you need on one side to lift another object. If we know what the weight of that object is, if we know how long a lever arm it has to the fulcrum, if we know how much more lever arm we have on our side, we can use that equation to determine how much force do I need to apply to the other side to lift this heavy object. So we see from that equation that when the two products are equal, F1 times D1 equals F2 times D2, the two sides are actually balanced. If we apply any more force or any more distance to one side, that side will then go down, lifting the other. What we also notice about this equation is the form of the product, F times D. So those two have what we call an inverse relationship. Imagine we have a situation where two sides are balanced. Force 1, force 2 are balanced based on lever arm lengths D1 and D2. Now if those are balanced, and if F1 increases, you add more weight to that side, well, they won't be in balance anymore. They'll come out of balance with F1 lifting F2. So what has to be done to compensate for it is that new F1 has to be brought in closer to the fulcrum, which means D1 gets shorter. So if the force increases, the distance has to decrease on that side to compensate for it. That's an inverse relationship, and that's going to be important in what we see when we do our measurements for leverage. If you see in the case where F1 is greater than F2, and if D1 is also greater than D2, now what's going to happen? Well, the product of F1 and D1 is definitely going to be greater than the product of F2 and D2. In that case, F1 has more leverage and more weight, and it will definitely lift the other side. So that will be definitely out of balance. For them to be in balance, if F1 is greater than F2, we're going to need D2 to be greater than D1. So if F1 is greater than F2, D1 has to be smaller than D2. Let's start with an example where we know the force on one side to be balanced. Let's say it's 2 pounds. Let's say that we know the distance that it has to the fulcrum, the lever arm length on that side where the 2 pound object is resting. Let's say that's 4 feet long. We also know that the force used to balance it on the other side is 1 pound. How long would D2, the distance on the side where the 1 pound object is, how long would that distance need to be? How long of a lever arm would we need in order for the two to balance? Now, before we do the computation, let's think about this. Let's formulate a hypothesis in our minds based on what we know. Remember that the force and distance, the product of force and distance, represent an inverse relationship between the two. And we know that one side, the object on side 1 is 2 pounds. The object on side 2 is 1 pound. So force 1 is greater than force 2. The distance on one side is 4 feet long. So what would we expect to happen on the other side? Would we expect D2 to be greater than D1? Or would we expect D2 to be less than D1, given that force 1 is greater than force 2? Think about it, and let's return back with a computation. Okay, let's do that computation and see if it matched what our hypothesis was for what D2 would be. So on the left side, we have 2 times 4. Force is 2, distance is 4 feet. 2 times 4 is 8. And on the right side, we have 1 times something. So 8 equals 1 times something. What is that something going to be? Well, 8 feet, of course. How did that match your hypothesis? We knew that force 1 was greater than force 2, and the distance that force 1 had to the fulcrum was 4 feet. Knowing that it has an inverse relationship, we should automatically expect that distance 2 on the other side will have to be longer than 4 feet. Let's take one more look at that equation and see if we can notice something else. 2 pound object balancing a 1 pound object. The 2 pound object had a 4 foot lever arm, and the 1 pound object had an 8 foot lever arm. The object on side 1 was twice as much as the object on side 2, and the lever arm on side 2 was twice as much as the lever arm on side 1. That's the nature of that inverse relationship that we were talking about before. So we should always expect that if the force is lighter on one side, in order for that to balance, it's going to have a longer lever arm, and that lever arm is going to have to be longer than the other side by the same multiple that the force is larger on the other side. Let's do a second example, now using metric units. Let's say we have a 20 meter long lever arm, and the fulcrum is 5 meters from one side, 15 meters from the other side. On side 1, we've got a 6 Newton object. Now, what's a Newton? Well, Newton is a standard measurement of force in the metric system. Some people think of kilograms as weight, as a measurement of force in metric, but the reality is that kilograms are a measure of mass. Newtons are what we use to measure force in the metric system. So we have a 6 Newton object with a 5 meter lever arm on one side, and we have a 15 meter lever arm on the other side, but we don't know the mass needed in order to balance that object. So what do we think? Again, formulate your hypothesis and think about the relationship in the two distances we have. 5 meters of lever arm on one side, 15 meters of lever arm on the other side. So think about what the force would need to be on the longer side in order to balance that 6 Newton object. Running through the multiplication, we see that we have 6 newtons times 5 meters. That's 30 Newton meters on the left side. equals something times 15. So what would that something need to be to equal to 30? Well, 2 times 15 would be 30. So we know that the force on the longer lever arm side needs to be 2 newtons in order to balance the two. And now let's go back and check to see if it makes sense. The distance on the heavier side was 5 meters. Distance on the other side was 15 meters. 15 is 3 times 5. So what do we expect to have happen with the two weights? Well, we have the shorter side having 6 newtons. We expect the longer side to have a weight that's 1/3 of that 6 newtons, just like 15 is 3 times 5. Therefore, we get 2 newtons. So it all matches up. The 2 newton object is 1/3 of the 6 newton object, and the 15 meter lever arm length is 3 times the 5 meter lever arm length of the heavier object. So it all works out using that inverse relationship. Let's do one last example. Here we have to determine what the distance is for a heavier object that's weighing 14 newtons. The other object on the other side is 4 newtons. That 4 newton object has a 7 centimeter lever arm length. So how long would the lever arm be on the side which has 14 newtons? Again, formulate your hypothesis, and then let's do the computation to see if it matches. Because the 14 newton object is heavier than the 4 newton object, we'd expect that 14 newton object to have a shorter lever arm length than the 4 newton object does. Going through the math, we see on one side we have 4 newtons times 7 centimeters, 28 newton centimeters. And on the other side, we have a 14 newton object times some distance. 14 times what would be 28? Of course, that's 2 centimeters. 14 times 2 centimeters, 4 newtons times 7 centimeters. Those two would make it balance. We expected that the 14 newton object would have a shorter lever arm length than the 4 newton object did. And if we look a little more carefully, we can see that 14 is actually 3.5 times as much as 4. So therefore, the 7 centimeter length needs to be 3.5 times much as the lever arm length on the other side, which is 2. So again, it all balances out. We've used theory to calculate the force and distance needed to balance objects. The next step is to run a set of experiments to really confirm that mathematical model. In your Trebuchet Design Steam Kit, you'll find 2 fulcra. Let's take out one of those, and it should have a red stripe on it like this. Take that fulcrum and place it on a flat surface just like this. Next, take out the lever arm from your Steam Design Kit. Notice that there are little tick marks all along the lever arm. Those are about 1 centimeter apart, and we'll use those to measure the distance from the weights we hang on each side to the fulcrum when we balance it. Speaking of weights, you'll see that there are 3 sets of weight in your kit. One with 4 washers on it, one with 8 washers on it, and one with 12 washers on it. Let's start with the 4 and 8 and hang those on each side of the lever arm while holding the lever arm in our hands, just like this. Using 2 hands, carefully lift the lever arm and place it on the fulcrum along the red stripe. Start with a position where the 2 sets of washers are roughly equidistant from the fulcrum, and then slide it around until you see the 2 weights balance. In this case, I'm able to get the 2 weights to balance at this far apart. So I'm going to count the number of ticks from the hook to the center of the fulcrum on each side. You'll be recording your measurements in the provided worksheets. We'll use object A for our first experiment as a set of 4 washers, and object B as a set of 8 washers for the first experiment. So we'll record 4 under the column of number of washers A in the first experiment, and 8 for number of washers B. Now we need to count the number of centimeter tick marks from each side to the center of the fulcrum. So I'm going to start with side A and count, not counting the tick mark where the actual object is. So I'm going to start one over from that, so that'll be my 0 mark where the washers are hanging. And I'll start to the right of that, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 to the center. For object B, again, I'm not going to count the tick mark where the object is hanging. I'll start to the left of that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 centimeter tick marks. So I'll record in my worksheet 21 for the length of for the length of the lever arm for object A, and 11 for the length on side B. What did you get for your measurements? So observe the data that you recorded and see if it makes sense. Object A has a lighter weight, fewer washers, than object B. In fact, it has roughly half the weight. Object B is twice as heavy as object A is. What do we expect for the length of side A? We expect it to be roughly double to make up for the fact that the weight on the other side is double. I got 21 tick marks and 11 tick marks. 21 is roughly doubled 11. Double 11 is 22. I got 21. That's corroborated by that equation that we had talked about before. Force times distance on one side equals force times distance on the other side. Now, I didn't get exactly double, and we have to wonder why. Well, this is where experimental error comes into play. As we see here, our fulcrum is not a perfect point. It's flat, which means I can get the object to balance by moving with the lever arm, one tick on one side, one tick on the other side, and those errors are going to go into my measurements. So I might have plus or minus 1 centimeter error in each of my measurements. 1 centimeter of error on one side, 1 centimeter of error on the other side, so I might even get up to 2 centimeters of error. As long as my measurements are within that 2 centimeters, those measurements still corroborate the mathematical model we had seen before. After this first experiment, we'll do 2 more experiments. One where we have object A still remain as 4 washers, but we'll use object B as the 12 washer set. Again, we'll slide the lever arm around until we see the 2 weights balance. For our third experiment, we'll replace the 4 washer side with 8 washers. Again, make sure you hold the lever arm firmly when you replace those weights, and then find the point at which the 2 balance. Each time, record the distance from the set of washers to the center of the fulcrum and put that into the worksheet. Let's see how well the measurements you get line up with the mathematical model. Great job successfully completing the experiments. In all the experiments, we saw one common theme. That is that the lighter object needed a longer lever arm in order to balance the heavier object. Now we're going to assemble our mini trebuchet and have a little bit of fun. First, let's take the weights off of each side of the lever arm, place them aside. Next, we need to find the metal rod that's in the steam kit. Insert that metal rod through the lever arm first, and then insert it through one of the bases. Let's find the other T-shaped base. Again, we should see a hole on one side, and we'll insert the other side of the lever arm, other side of the rod through that base. We should have something that looks like this. The lever arm should be able to rotate freely around this rod, and the 2 bases should be holding tightly to the rod as well. Okay, we're almost ready to launch. Notice how the rod is now functioning as the fulcrum, our lever arm is able to freely pivot around it, quite cleanly in fact. Let's take the set of 4 washers and use that as our first weight, hanging it on the end opposite where the cup is. And let's get our marshmallow. This is going to be our projectile. Hold down the lever arm with one finger, load up your marshmallow, and get ready to launch. When we remove our finger, we should see our marshmallow pumpkin fly across the room. Ready? 3, 2, 1, go! That was pretty good. I wonder how it'll react when we try 8 washers or 12 washers. When we use the heavier weights, we may need to also hold the base of the trebuchet down to make sure that we get a good clean launch. It's going to be a lot heavier. So hold the base of the trebuchet with one hand while holding the marshmallow with the other hand and launch again. How far did it go with each of your different weights? Let's find out. Congratulations on completing the Trebuchet Design STEAM class. Hope you had fun and I hope you learned a few things. Please share your feedback with us. We'd love to hear it. Until then, I'm Tushar Murthy with STEAM Explore and Design Thinking. Happy Punkin Chunkin.